Yo, what's popping, gamers? It's jumpVids here. I'm back for another episode of this. I have 2 viewers. This is unheard of. I better get started before people get bored and leave. Oh my gosh. So, as you can see, my webcam is incredible lighting as always. Usually my lighting's okay, but I just did not think this through. There's a bright window behind me, and I haven't got any lighting to add, so I'm just a silhouette this time. So that's fun. I might turn my webcam off if feel like in a bit. Has anyone in chat can type or anything? Say hi. If so, that'd be cool. What do you think about the silhouette webcam? Do I turn it off? Do I leave it just as a weird shadow? I don't know. I think I'll just leave it, to be honest. So yeah, today we're looking at mathematics. Where's my slide? So originally the title was going to be summarizing about 50% of my mathematics education as of right now. In the end, I fancy putting cake and the hidden textbook in the title, so I had to change a bit, but this is what we're going to be focusing on. So I do 2 maths courses side by side because I'm a bit crazy like that. And essentially I just wanted to like go through my textbook in terms of like the topics and like explore each one. But the thing is, I didn't like how my textbook like divided up the topics, so essentially I've like reconfigured it. So the textbook had like 22 chapters, but then I like reconfigured it so I've got like 19 components instead, is how we're doing it. So yes. Where's my things? Oh my gosh, what a mess. So basically 19 components, and it's split into 5 sections. So we're going to be looking at quite a bit of pure maths. So we got pure calculus, algebra, and we got pure linear algebra. We're only going to be looking at a small bit of linear algebra though, because it's kind of complex, and the textbook only goes into like one small area, which is vectors. But other than that, no more linear algebra, unfortunately, which is a shame because I really like linear algebra. It's one of my favorites. Gonna be doing what I've decided to call statistics 1. I should have just called it statistics, but it is what it is. And then the most legendary of topics, almost physics, subtraction, Newtonian mechanics 1. Yeet. Oh, I lost a viewer. This is so sad. I'm kidding, it's fine. Oh, it's so sad when you have viewers but they can't type in chat. F's in chat, boys. Alright, so these are the 5 things littered around like a great mess that this is. Wait, I just realized I want to list things under it. I should have done it more organized than this. Oh well, why am I numbering them? No one cares. How can I save this? I know, I'll just copy paste. That'll be fantastic. But there's a lot that goes into, where is it? All that goes into this first topic anyway. Alright, I probably should have wrote these out beforehand, but I'm not very clever. I'm going to do it on text edit instead because I'll make it quicker. Yeet. Ah yes, as prepared as always. It's funny, I actually did prepare for this stream a lot. There's like, what can I show you? I'd probably show you this. Oh wait, no, but you can't see on my webcam. This is tragic. Maybe if I get some lighting. Wait, let me do this at the same time. Alright, how do I make it bigger? I should have thought about this. Is it in here? It's probably in here. Oh my gosh. The confusion. Alright, let's make it huge. 48. No, let's go bigger than that. 64. So hopefully if I... Oh yes, this is the size we need. Alright. That's probably too big actually. Oh, why is it so slow to go in here? No. Okay. There we go. There we go. So component 1, 2 are notation. Component 3 is methods of proof. Looking at 3 of those. Component 4. Oh yes, only the most exciting of topics. Exponentiation Basics. It's a topic where it's like it's really important and it's not obvious. You wouldn't be able to know about it unless you explained what it was. But like I feel like no mathematician wants to talk about it because it's like so. It seems really basic, but the thing is, I know it's not, and there's no way of knowing unless you explain it to someone. Polynomials, poggers. Component 6. Graphs are Pokemons. That's literally what I've named that component. Other skills of graphs. I don't know how many I'll get through today. I've got until 10, so I've got 34 minutes. Let's go. Pog. Further exponentiation. Let's just call it logarithm. There we go. Quad geom. Everyone's favourite, coordinate geometry. Very fun. I'm just going to call it byte. No, you're not. I have to put a little bit more detail on that. There we go. Yeah, let's leave it at that. Go look at trigonometry. Look at calculus. There's so much stuff. What the heck? This is going to be fantastic. And then within linear algebra, we're going to be looking at vector notation. Yeah, let's go with that. Vectors. And you know, we can worry about the rest. This is all the pure stuff. Oh my gosh, it's huge. On my head, I was like, oh yeah, it's nothing, but it's kind of a lot when you expand it out. Grab some water. Oh, I've got an epic water station over here. You can't see anything though, because I'm just a silhouette. I am nothing but a shadow. Hydration. Wait, is my audio going through? I hope so. Yeah, it's going through. All good. All right, so I don't know how much I'll get through today. I guess I wish I could draw on this. I probably can draw on this. If we just go, boop. Oh gosh. Like that. And then if my computer doesn't take a million. Okay, it's not liking that. If we go slightly less than the whole screen, it'll probably like it. Technology is weird, man. Hopefully it won't take a million years to save. Oh wow, that is some serious lag right there. We need to save up some memory. Memory, don't leave me. Polynomial. There we go, now I'll be able to write on it. Yay. Computer science, woo. My favorite. Okay, so if we go in here, we dump that there. Whoa, it's magic, we can write on it. Oh my gosh. Ugh, that was pretty long-winded. Just because I'm only writing a small bit. So this bit's really fun. One of my favorite areas is maths notation, not even doing maths, just talking about how to notate it. Incredible. Proofs is a hard one to communicate. I might give it a pass and come back to it later, because I haven't done really any preparation for it communicating that specific bit. This bit I have no idea how to communicate. I might just give it a go just because it seems fun. And this topic's great. Polynomials is pretty good. It's not too hard. Although to make it exciting is a bit hard, but the goal is not so much exciting as to just dump all my ideas into this one video about these subjects and stuff. And then later on I can like re-go over sections, but like in more detail and with more care. Alright, let's do this. Component 1, component 2, notation. So I guess the big question is, why is it not one component? Why 2 components on notation? And earlier I was like, oh yeah, I have a good reason to split into 2 components, but right now I'm like, should just put it all together. Yeah, we'll see. We'll see if the split makes any sense. All right, 1, 2. And of components 1 and 2, we're going to start with component 1. So we're going to be looking at different ways of notating things. So the things that we want to look at is like inequalities or ranges and how we notate that, and then go look at a small bit of set theory notation, and then we can look at some super technical like operations versus operators. I'm going to write that here because I feel like it. Because you might think that operations, right, and operators. Let's do it like that. Right, like you'd think they're the same thing, and I pretty much always thought they were the same thing. Turns out there's like actually a pretty important difference between them, so I guess we'll be looking at that. There we go. Amazing. All right, let's start with a good place to begin. Start with the number line. Everyone's favorite. And right in the middle, we have 0. As most people are aware. And you can go up the positive integers here, so that might be 3, over here might be 6. And you can keep increasing by any amount, so any finite amount, sorry. So we go by 3s or by 4s or 5 or whatever. Or maybe 17 up, 6 plus 17, 23. the point is you can keep increasing here, and while you can never hit what's at the very end, we can sort of talk about the fact that over here we'll have like infinity, right? You can approach infinity that way, or positive infinity, I should say. And here you've got stuff going on over here too. And why I'm doing this will make sense in a bit, hopefully. I have pure faith, oh my gosh. Then we can approach negative infinity this way. Very cool. And essentially what we often need to do in mathematics is talk about which of these numbers are important in a given situation. So I should probably give an example for that because that's pretty abstract. Like say for example, we have a quadratic that looks like this. Boop, boop, boop. We might want to talk about for the quadratics, let's say the quadratic's like this, which values of x give a output value f of x that is above the x-axis, so it's above this axis here. So it could be all of it. If the quadratic, let's say the quadratic was here, we would say for all values of x, it's above the x-axis. So in that case, we'd say that it's above the x-axis for all of x of the set of real numbers, which is essentially just the entire number line all at once. But sometimes we might want to talk about numbers more specifically than that. So for example, let me rub this guy out. No, I won't. I'll keep him in. Give him a color. Purple. Whoa. There we go. But then for this guy here, clearly it's not above the quadratic's not above the x-axis for all values of x. It's only valid for these ones here. And also, let me highlight it on top. Let me choose a different color as well, actually. Not having any chat participation is kind of sad. Rib. So you can see it's above the x-axis for all of these values. So if we knew where it intercepted, which in this case we'll say we do, because in general quadratics will have like your formula, right? I know we're not writing that out, it takes too long. So this might be -3, this might be 4, so we need to say it's above the x-axis for -3 or greater. No, -3 or smaller, sorry, and +4 and higher. So on here, this is 4, we need to talk about the values that are 4 or greater. And because in this set of numbers here, 4 is included, it means we shade this circle. It's just convention. Because sometimes we might have bigger than 4 but not including 4, in which case we wouldn't shade it in. Because 4 is included, we'd do that. And then over here, that's -40, I see. I see. And this is -3, say. Then we could say we're including -3 and smaller. So you go like this. So this is one way of notating a set of values, is you can just like draw on the number line. The thing is that would require drawing a number line each time. It's kind of slow, and often we need to talk about which numbers we're talking about, which numbers we aren't. We need to talk about which numbers we are or aren't including much quicker, and it takes too long to draw the number line. So we have three different ways of doing it. So one way we could do is we could say x is smaller than or equal to -3, or I guess this is what we call inequality notation or whatever. I don't really like this notation, but some people do. Some people will use this notation like the entire time. The thing is, that took kind of a while to write out, and actually the notation I like, which is called set notation or set interval notation, actually takes a similar amount of time. Feels quicker in my head though. And the way that would go is it would go negative infinity to -3. And then instead of writing the word or, we'd use a symbol for or. So we'd go symbol or, and then +4 up to infinity. And this seems kind of mundane, but talking about this notation is quite useful because it's quicker to write later. So we're going to be using this notation like exclusively because it's just, in my opinion, so much better than this way. And the other way you could do it is you could do it using set notation, but set notation is just, I mean, not set notation. No, it is. Is this interval notation? I don't know what they're called. No one really cares what they're called. We'll just call them method 1, 2, 1, 2, 3, 4. So that's method 1, using the number line stuff. And then number 2, draw out your inequality signs and whatnot. Number 3 like this, which is the method that I really like and I'm going to be using pretty much only because I think it's way better than this notation. And then the other way you could do is, I'll do a different example for the 4th method you could use. Let's say we were talking about all numbers that are x bigger than or equal to 4. The notation you could use is you could say the set of x such that x is bigger than or equal to 4, but it's like so irrelevant. It's like, why did we write all of that? You might as well have just written this, right? Someone can probably defend this, why you'd ever use this. I think if you add more parameters, like this is x such that, but you can add more parameters. Say x such that bigger than or equal to 4, and then add a second parameter here. So more complex set theory stuff, it's useful. But right now, it's kind of irrelevant, not going to lie. All right, so basically all these methods are irrelevant except for method 2. One's occasionally good, except for method 2 and method 3. Method 2, a lot of people like, I don't, so I'm pretty much going to be using method 3, but a lot of people don't know about method 3, so hence why explaining it. I should probably go into more detail so that it's clear exactly how this works, but I kind of want to move on. Or I could just use this notation, just so I don't have to use this and people won't know what it is. I might draw both whenever I need to do ranges, but this method is honestly, I should just do a video on that. It takes longer to explain than I thought. In my head it's like, oh yeah, it'd take 2 seconds to explain it, but already all of this felt like it would take 2 seconds. It took way longer. Alright, good to know. What else is there to talk about? Oh, we could talk about operations and operators. Operators comes into calculus, but other than calculus it doesn't really appear anywhere. Is it worth talking about now just because calculus really isn't, so maybe we just move on. I was going to talk about some more set theory things. Can't decide if I'm going to now. Things just take so long. I guess we can talk about this. So, so a set you notate with this curly thing, and it contains a number of things, usually numbers. So I might have a set of 3, 4, 5. Maybe we'll call this set y. And then if we wanted to say something was of y, say we wanted to say 4 is of the set y, you can use this symbol here, and that just means of the set. So it's just like a collection of things. So 4 is of the set y. It's most useful for if you want to say a variable is a certain thing. So let's say we have the equation x plus 5 over 16 equals n, but we need to specify that x is only ever going to be an integer. Instead of saying x is an integer, it takes a while to write, we can just say x is of the set of the integers. So in other words, x is an integer because z represents this special character z represents all the integers, so it's like 0 and then positive 1, positive 2, etc. in this direction all the way up to positive infinity, and then negative 1, negative 2. So it's infinitely sized set. It contains all the integers, so if x is of this set, it must also be an integer is the idea. There are a few different symbols, so we have this z one here. There's a bunch of others, so you have n for naturals. I'm just trying to decide if I need to go into all of them, what a natural actually is. Then we've got z, which is integers, q, which is a rational number. It doesn't get used so much, I don't think. R, which is a real number. And there's also a C for complex numbers, but complex numbers are outside the scope of what I'm doing today. Too complicated, hence the name complex, I guess. This is just any number. So like I said before, so if it's any number on the number line at all, it's R. And then I guess I'll talk about naturals quickly. So naturals are the integers, but just 1, 2, and greater. So 0 doesn't count, -1 doesn't count. I won't talk about q because I can't be bothered, and I need the time. 20 minutes left, let's go. We've covered a lot of notation, this is good. It's going to be this entire video though, of covering just ridiculous amounts of ground. Okay, was there anything else that I needed to cover in this? I was going to talk about this symbol. This symbol isn't very conventional, but I really like it. It basically just means there's something that connects these two. They're related in some way, or they oppose each other, or something like that. Just in general, it's quite a nice symbol. It's not really conventional, and no one ever really uses it, but I really like it. It's quite nice. So if you say A is kind of associated in some way to B, I think it's quite a nice symbol, so I'm going to be using it quite a bit in terms of notation to talk about. And then what other notation is there that should probably be talked about? I was going to talk about ln being equal to log of e of a number, but we can look at that when we look at logarithms later on. So don't need to talk about that too much here. And then there was one other thing. Oh yeah, you can do, so let's have equation x plus 5 equals 0. We want to say another equation is equivalent to that equation. We can use this symbol. It's kind of an irrelevant symbol. You don't really see it so much, but sometimes it can be nice to use in working out. There's also one-way arrows, but those are really confusing to understand what they mean, and no one really cares. So, I mean, I should probably care. Other people should probably care, but like, honestly, it's like, nah. It's easier just not to deal with that. There's not many times when you really need it, so you can honestly just ignore it. It's fine. So what we can say here is we're saying the two are equivalent. So, and what it really means is this implies this, but this also implies this. But that's confusing to think about too, so it's just the two are equivalent. Sometimes you can't use this symbol because one way is true but the other way isn't. But if they're equivalent and you can sort of see you can go from there to there, and you could also go from there to there, then you can use this symbol to say the two are equivalent. Sometimes is useful to use. All right, that was a pretty successful covering of component 1 and 2, I would say. Give that a big tick. Oh, I kind of want to talk about methods of proof. It's just this, it took a while because I hadn't prepared anything. Like this, it will definitely take a long time without preparing anything. Or maybe I just want to talk about the types. No, I don't. I want to prepare more for that. So we'll go on to exponentiation basics. All right. What do I mean by exponentiation basics? Great question. So as most people are aware, oh, one other notation thing. No, this is an important one, so I'm going to talk about it. Even if it means being slow. Oh no. Oh no, this is so slow. Oh gosh. So many pages. You know what, we'll just ditch it on any old page. Essentially, I like to use a square for a number. It's like an input. So for example, if I was talking about addition, I'd do this to be something goes here plus something goes there. And honestly, like, I love this notation. I've never seen anyone else do anything like this in terms of notation, but it's so cool. For me, at least, I feel like it's really clear. Way better than using variable names or anything else, really. I guess, nah, this notation's awesome. So I'm going to use it. It's not conventional, but I use it a lot. So just putting that out there to make sure people are with me when I'm using that notation. You know what, let's just make a new one. All right, exponentiation basics, let's go. So we're all aware that there are 5 main operations in an algebra. So you got your addition, which takes in 2 inputs like so. Or you got your subtraction. You got your multiplication, and there's also division. Oh, and there's a 5th one. And some people would say there's also square rooting. This is exponentiation. And then we've also got, some people would say square rooting is one, but in reality this is just exponentiation, as we'll look at very soon. So in reality this is kind of relevant. There's also logarithms, which are a 6th one, but people don't tend to know about these as much. So just kind of throw it in here, but we'll talk about logarithms more later. Maybe not in this video, but definitely later at some point. Oh my gosh, so much maths. I didn't bring enough water. Oh, I'm a shadow, aren't I? Oh no. So exponentiation, for some reason, it always scares people when you call it that. Even though they know what it is. A lot of people know what it is, but get scared by it being called that. I don't know why. An example is 4 squared. So most people, if you get asked them to evaluate 4 squared, they'll be able to do that and tell you it's 16. So they therefore know exponentiation, but for some reason, calling it that sort of makes them go, "What's exponentiation?" But it's not not difficult. Well, it is difficult. Understanding it's difficult, but understanding the essence of it isn't too bad. So 4 squared is 4 exponentiation 2. Most people are comfortable with 4 exponentiation n, where n is any natural number, which, like we said earlier, is 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. But you can actually do exponentiation where n is any rational number q. Oh, I said I didn't go into q earlier. I guess q is useful. A rational number is just any number that can be expressed as a over b, where a and b are integers. So for example, 17 to the power of 4 over 5, even though this is a lot scarier, 2 ways you can evaluate this. Either you can know about this topic, exponentiation basics, and how to evaluate that, or you can just shove it in a calculator and that'll give you an answer too. But either way, you can do that. And I'll shove it in a calculator now, I guess, just to see what we get. 4 over 5 gives us approximately 9.6. So that's exponentiation. Scares people, but it's not too bad. For this sort of collection of mathematical things we're looking at in this here video, and maybe series of videos, depending on how I feel about this, is we're only going to be dealing with a fractional / rational number exponents, because if you do irrational numbers, say we did 17 to the power of pi cannot be expressed as a over b, where a and b are integers. Evaluating that is a lot more difficult. I mean, again, you can just shove it in the calculator, it'll give you an answer. But in terms of evaluating it by hand, this is quite tricky if you want an exact value, especially. So that's the thing. All right, let's look at evaluating some exponentiation by hand, where we've got a fractional exponent. All right. So let's say, for example, we want to do 4 to the power of 5 over 2. And what we're going to need to do this is we're going to need to know some exponentiation laws, which is what this section is all about. Things that are true. Proving them can be a pain sometimes, but you don't really need to prove it a lot of the time. You can just sort of accept it's true and use it. So first rule we're going to look at, I guess, is that a to the power of b all to the power of c is equal to a to the power of b multiplied by c, and vice versa. This is quite useful because what it means is for any number that can be written as a product of 2 numbers, which is like any real number, any real number. Yeah, any real number at all. I was going to say, can I do that with pi? But you can do it with pi. Just it's weird with pi. Any real number. So for example, 5 over 2, we can rewrite that as 5 multiplied by 1/2. You might be like, well, why bother? Who cares? But that's actually quite useful. And essentially exponentiating, where you've got a fractional exponent like this, is you need to split it up into to the power of 5 and to the power of 1/2 to do it. So let's do that using this law, which I guess I'll call law 1. Wow. They don't really have names. The thing is although it seems kind of tricky at first, eventually it gets to a point where you just know them intuitively because you just use them so much. So we can rewrite this as 4 to the power of 1/2, and then whatever result that gives, I'm going to raise that to the power of 5. And then the next law we're going to look at is for any value called x, it really doesn't matter, to the power of 1 over q, where q is of the set of integers. I should have just written a z, I shouldn't have bothered with the fancy z. Oh well. Equals the cube root of x. And hence why earlier I was saying there's no point including this as its own operation, roots, because roots are just exponentiation. Anytime you've got a root, it's the same as raising it to the power of 1 over that thing. So if you take the second root, that's the same as raising it to the power of 1 over 2. Or a cube root is the same as raising to the power of 1/3, 1 over 3. Yay. So here, it's the power of 1/2, so you take the square root of 4. Square root of 4 equals plus or minus 2. Whether or not you need both roots depends on the situation. Here we'll just like assume positive. I guess I'll draw that to mean we're going to assume that we're only taking the positive root just because it's less annoying. So we're only taking the positive root, so we're just going to take positive 2. So that leaves us with 4 to the power of 5 over 2 equals 2 to the power of 5. 2 to the power of 5 just means take the product of 2 5 times. So if you take the product of 5 lots of 2, then you get, you can just shove it in a calculator or just know that that's 32. And there we go. Is that all we need in Exponentiation Basics? Is there anything else? I have textbook here. I don't like using textbooks, so I kind of don't want to look, but I also do. Is there any other rules that are worth knowing about? I think I got the main ones, surprisingly. I'm not going to number them from now, I'm just going to think about what other rules there are. The other rules are you have like b to the power of a, take all of that and multiply it by b to the power of c, and it's always equal to b to the power of a plus c. It's quite a nice rule. That's about it, really. There's a few other small ones, but honestly... Oh, no, there's an important one. There's an important one. R, by the way, R is just any variable name. All the variables are just whatever. Just give it a variable name. No one cares. R to the power of negative 1 is equal to 1 over R, which is like really useful. Oh, and similarly, for the same reason, actually, but we're not going to go into the same reason. You might be able to see why it's the same reason. Essentially, these are the same law. I'm just rewriting it in a different way. But this is equal to b over a. So you flip the fraction. We call this the reciprocal. So b over a is the reciprocal of a over b. Those are quite useful. And again, basically all of these laws are sort of assumed for like the rest of maths itself, really. So important stuff. Oh gosh, I didn't bring enough water. What the heck? I got through all my water already. Oh my goodness. I can't tell if this is... I mean, for me it's fun, but I'm like, is my audience gonna find this fun? No chat is actually depression. I guess I should have chose a cooler topic than maths. Where's my list? Is my list gone? Yo, there's my list. Or I can have it with writable. Alright, we're done with Exponentiation Basics. That was fun. This topic's really fun. Methods of proof, like actually fun. Hopefully I'll be able to prepare something cool and talk about that. Interestingly enough, what really brought this topic alive from the textbook is the fact there were mistakes in the textbook. Almost to the point where I kind of want there to be mistakes in maths textbooks because it's actually cool. Where essentially where you get together in a class and you're like, you look at the mark scheme and you disagree with it, and it forces you to convince the teacher and to convince other people that the textbook answer is wrong. You have to use proofs. And so by being given a mark scheme with intentionally wrong answers, to force students to create proofs to show that it's wrong is like actually a really strong way to show proof in action. That's really what proof is for. So where someone else is wrong, well, if you tell them they're wrong, they might be like, no, I'm right. But if you construct a proof, you have to show them that they're wrong. And that's like really where proof's at. So essentially using that and a few other things, I'll do it like a more proper section on methods of proof another time. But that's sort of the rough idea of proof. Proof is such a cool topic in maths. These are both pretty dense topics, but I got through them today, so I don't have to do them ever again. Yay. Alright, moving on to more fun stuff. Polynomials, poggers. Polynomials are sick. Alright, this is slightly less dense. Oh, and also alongside the component for Exponentiation Basics, we looked at the oh, where is it? No, please, I need this. We looked at the 1, 2, 3, 4, 5, 6 different operations of algebra got going on here. These are going to be useful, especially when we move into polynomials. Alright, let's go. So a polynomial links onto functions. We haven't spoken about functions, but if you made it this far, then you probably already know about functions. But if you don't, then hey, let's talk about functions. So essentially, if you have an expression, say 5 squared plus 4, then you just evaluate it out, and this is a calculation and no one cares, it's fine. But if we introduce variables, like say x to the 4 plus 7, instead of all values, now there's a variable, and what this means is unless we know the variable, we can't figure it out. So what this describes is a value, because you can evaluate it straight away. There's like no uncertainty, I guess, is the way you could think about it. You might not necessarily immediately know what value it is, but you know it's going to be a value. Here it's going to be 5 squared plus 4, which is 29. But the point is, because there's no variables and it's just a collection of numbers and operations, it's going to be a value. So even though it might look kind of function-y, it's not. It's just a number expressed weirdly. And so what that means is, like, on the number line, if you have 3, an alternate way you could write 3 and it would be the same point on the number line is 2 plus 1. So 2 plus 1 isn't, like, sometimes people call it like expressions, or yeah, a lot of people call them expressions, but really it's just an alternate way of writing 3. I think is a better way to think about expressions without variables. It's just a weird way of writing another value. Whereas this isn't just a value. This isn't just some number written weirdly. This is, I guess, what we could call a process, or, as I'm telling you now, as we call it in mathematics, a function. Because what we got going on here, or more specifically a mapping, but no one cares about mappings. I kind of care a lot about mappings, but I haven't got time to go into it. So we'll just assume mappings and functions are the same thing for now. They're not, but close enough. So this is a function. This one's actually a function, but some things like this, for example, root x plus, say, 11, technically isn't a function. It's just a mapping, for reasons we could go into. But for now, we're just going to call it a function. It's honestly, no one cares. It's fine. All right. Function, because essentially what we're saying is this is a thing you can do. 2x, we could do this, and we tend to give it a name. So the most default, in the same way the most default variable name we tend to use is x, most default function name we tend to use is f of x. You could just write f equals this, and sometimes you do. You see this a lot with, say, y equals x squared plus 7. That's essentially just saying function y is equal to an input x squared plus 7. Or you can give it a name and say with respect to what. So this is a function that's going to act on an input that we've named, and we're saying that is the input x. So they're just two ways of writing the same thing. And there's advantages, disadvantages. So this has the advantage of it's quicker to write y equals something than it is to write f of x equals. But this has the advantage of the really cool notation you can do where you show it being used. So if we say function of 2, because we've written our input here, it means you can see the input going in. And it's just cool. Like you don't get that with this. If we input y, if we input 2, you don't see it going in like you do here, which is super cool. So hence why this notation honestly is the superior notation. Writing f of x is way more fun than writing y, to the point where y is kind of irrelevant, not gonna lie. Just kidding, y is everywhere in maths, it's fine. Because you get coordinates x, y. But really, you could do coordinates x, f of x. And in higher mathematics, you tend to see that more, I think, than x and y. I think. Is that correct? I don't know. Y and f of x both get used. They're good in different places, basically. So we can evaluate this out. 2 to the power of 4 plus 7 gives us 23. So that's a thing. So anything without a variable is a value. It's just a weird way of writing another number. Whereas if we use a variable, we have a function. And you can put multiple inputs in for a function. So you could have f of both x and y equals, I don't know, what do I want? Equals x squared subtract y squared maybe. And then you'd have to put 2 inputs in, you get your output out. But this would be called what's called a binary function or binary operation, whereas this we'd call a unary function or unary operation. Unary functions where you just take one input are far more common, so you'll be seeing more of this, I guess. All right, so that's functions. How does it relate to polynomials? Well, essentially, all right, I was told that I only had until 10 p.m. So at some point I'm going to be kicked out. It's just a question of how long until I get kicked out. It's fine, I can stop at any point, it doesn't really matter. So all polynomials are functions, but not all functions are polynomials. This is the phenomenon known as subsets. Polynomials are a subset of all functions. And essentially, when you have a function, and this is all unary, this is all in terms of one input. I'm just going to draw this out so it makes no mathematical sense, I just think it looks cool. All right, there we go. So essentially what you do is when you have a function x, there's a certain set of rules, and if the function follows that rules, we call it a polynomial. So an example of a polynomial is f of x. This is one of the most common polynomials we all know and love. F of x equals x squared plus 20. It's a quadratic and it's a polynomial. All quadratics are polynomials, but they're not the only polynomials. You get polynomials that aren't quadratics. Quadratics is just one kind of polynomial, and it's what we call an order 2 polynomial. You might be able to see why we call it that. If you can't, then fair enough. It's not too important right now. But I'm going to highlight exactly why. It's because of this guy here. But that doesn't fully answer the question. We probably need to talk a bit more to say why it's order 2, but essentially it's because of this guy right here. So I guess the more important question we should be asking is, why is this a polynomial? So let's look at that. Look at the rules of a polynomial. I guess I could write out the rules. How long does it take to type it out? I've never written out the rules of polynomials. Oh, I probably have before actually in my personal notes. A polynomial is any function that is the summation of terms in the form ax to the n where, and then a bunch of limits. Pretty sick. Okay. We can do fun stuff. That was pretty efficient. Oh yeah. As a function, when terms are in the form, we're all as the summation of terms in the form, yeah, where a to x to the n, by the way, looks like this. It's a multiplied by x to the nth power, and there are certain limits on a and n. So a must be real. There's a certain limit on n too. Oh yeah, and n must be, what's the rule for n? Oh, n must be an integer. That's the first rule on n. And we'll talk about what summation means in a second. It's not that bad. It sounds horrifying, but it's actually fine. Limits on n is that it must be an integer, and oh, we're going to be using set notation. Oh well, we talked about set notation not very much earlier, but I can talk about notation. Oh no, wait, I can just read out what it means. It means 0 or bigger, including 0. And I should have covered this more detail earlier, but I just realized how hard it would be to do that. But essentially, because we've got a square bracket here, that means including 0. If we had a curvy bracket, like say this would mean excluding 0. So 1 counts, but 0 doesn't count. But because we've got the square bracket, it means we include 0. And we're going up to positive infinity that way. So here, because we've got hello, always wants the room. I'll finish very soon. Yeah, as I was saying, 10 p.m. So here, because we've got two terms, where we got a as 1, that's a real number, and we got n as 2, and 2 is an integer, it's between 0 and infinity. This therefore is a valid term, so we give it a tick. And summation just means you add up those terms. So we got summation here, we're adding things up, so therefore this is all valid. And here it's 20, it might be like, oh, there's no x, therefore not all the terms are of this form, therefore it's not a polynomial. But it is, because this is actually, you can think about it as 20x to the 0. X to the 0 for any x equals 1. Although it's controversial when x is 0, but we won't talk about that. Essentially, we'll just declare 0 to the 0 equals 1 for this situation. So any power of 0 is 1. So therefore, this is just 20 times 1, just 20. This is 0 to infinity. This is a real number. Therefore, this is a polynomial. To be honest, polynomials are more fun when you've already got the basics like this down. But I'm assuming like 0 prior knowledge at all for this series, just because I felt like it. So hence why I had to go into all the depth of polynomialness. Polynomials are cool though. I think they're cool. Oh, I could have used Desmos. We'll do Desmos stuff later. So I don't know how people felt about this format. I didn't get any feedback from anyone. So I guess I'll try and get some feedback, see what people think. I might be doing more of this and go through all of the topics I sort of listed. I might not. I don't know. mean, I thought I had a pretty good time anyway, even if it was a pretty garbage video, I don't know. But either way, thank you so much if you... Oh, wow! Hello. Nearly done. So yeah, see you